Hello everyone, Mr. Newman here, and today we're going to talk about transforming quadratic functions. We've already done a tiny bit of transformations of lines in a previous unit, but this really goes all out, and we have lots of different things to cover, so let's get started. First of all, you need to recognize that the input of a function goes inside the parentheses. It's nice to remember, inside the parentheses, input. And outside the parentheses, we have the output. This is helpful because whenever we're changing the functions or transforming a function, whether it's inside or outside the parentheses matters. It does one thing if we're inside and another for outside. If it's inside, just like the input is the x value, it's going to affect it in the x direction. And if it's the output, it's going to affect it in the y direction. In other words, if something is being added, subtracted, multiplied, or divided inside the parentheses, the function or the graph and the points are going to change horizontally. But if it is on the outside of the parentheses, it's going to affect the graph vertically. Let's get some vocab down, then I'll show you what I mean. First of all, the parent function is what we call the starting function. That's going to be on this chart, that graph in the middle. You notice that I went ahead and graphed for you the parent function for all of these, and they're all x squared. So I'm going to label that f of x is x squared. A transformation is just a specific change to a function. For example, it could be a shift, a stretch, or a reflection, or a flip. A translation is a slide where the overall shape is unchanged. And a dilation is a transformation where every x or y value is multiplied. So we have two vertical translations. On this side of the notes are the translations, and on the other side are the dilations. So all of these, you could go up and down, or you could go left or right. Let me show you what that means with specific points. So notice on the top middle graph there, I took a point, the origin, and I slid it up one, or I translated it up one. You can do that with every single point on the graph, and now it helps to mark some guidelines. So you see I marked the points 1, 1, and 2, 4, and negative 1, 1, and negative 2, 4. Those are just the points that are easy for me to see and plot, and I'm going to slide each one of those up by 1 unit. When I do that, I have my new function. It's translated up 1. Now the way we write that is we write f of x plus 1. Notice f of x is the parent function. G of x is, we sometimes call that the child function or the transformed function, or even the image. But we'll use just g of x, or the resulting function. You could move a function down as well. You notice I again chose the blue points there on the parent function so that I have some reference points when drawing my new function. And I'm going to slide each one down 1. Now, as you probably guessed, the way we write that is f of x minus 1. Notice the plus 1 and the minus 1 when going up and down. That's on the outside of the parentheses. So we're affecting it in the y direction, or the vertical direction. So if all of those go down 1, we can plot our new red points, and there is our function translated down 1 unit. We can also translate left and right. Notice that would be horizontal, and that means that we're changing the input. So the way we're going to write that differently for left and right is that we're going to have the x, the change, be on the inside of the function. Now, on this one on the left here, notice I selected my 5 blue points again, and they're all sliding or translating left 1. I plot the new points, they all moved left 1, and I connect the dots. But the way I write this isn't what you would think. You see, if I was writing this, I would assume moving left, that's in the negative direction, I probably should subtract 1. But we write it f of x plus 1. So a few things to notice. First of all, notice the x plus 1. That plus 1 is on the inside of the parentheses. That's what told me I was moving horizontally, left or right. And it's not minus 1 like I thought. This reminds me of both the factors and the vertex form, where any kind of change that happens on the inside of the parentheses does the opposite of what you expect. So this is moving left 1, even though it's f of x plus 1. Similarly, if we want to go right, we would say f of x minus 1. Notice it's again inside the parentheses, and it does the opposite of what we expect. So let's go ahead and move those 5 blue points. We move each one to the right one, and we get our new resulting function of translating to the right one. So how do we remember this? Well, the output is y, and that means vertically. So if you're adding or subtracting to the outside of the parentheses, then you're moving up and down. However, the input is x, and that moves horizontally. So if you're adding or subtracting inside the parentheses, you're moving left and right. And the thing to remember is that the input does the opposite of what you expect. This will happen on the back too when we get to dilations. So plus moves to the left, minus moves to the right. Let's just try a few of these examples on your own. Did you get them? Well, let's look. F of x plus 3, that's going to translate your graph up 3. F of x minus 5 is going to translate down 5. F of x minus 2 is going to translate right 2 because the x minus 2 is on the inside, so it goes right or left. And minus 2 I would think would go left, but it does the opposite of what you expect, so it's actually going right. F of x plus 4 is also on the inside, so it's moving right or left. But because I would expect it to move right, the input does the opposite, so it's actually going left 4. Notice up and down are outside the parentheses, right and left are inside the parentheses. That's it for translations. Let's now look at dilations or stretches. Just don't forget, the input does the opposite of what you expect on the back as well. Now, we're stretching and shrinking these graphs instead of just sliding them around. Let's start with talking about what we could do. We could stretch it vertically, or we could do a vertical shrink. We could do a horizontal stretch or a horizontal shrink. So let's first start by looking at the practice examples. We're going to use the same words as before, input and output. So for example, in number 1, it's 2 times f of x. That's on the outside, that's an output. So that means we're moving it vertically. And as you might guess, if you multiply something, it's going to stretch it. So 2 times f of x is going to stretch it vertically by a factor of 2. On the other hand, when we divide by a number on the outside, that's not going to stretch it, that's going to shrink it. So it's a vertical because it's on the outside of the parentheses, vertical shrink by a factor of 5. Or in other words, by a factor of 1/5, because dividing by 5 is the same as multiplying by 1/5. Think of it as the graph would be 1/5 as tall as it would be. The next one, the 3x is on the inside, so it's going to be horizontal stretch or shrink. And I would think that 3, multiplying by 3, would stretch out a graph, but remember the input does the opposite of what you expect. So in this case, it's not going to stretch, it's going to shrink by a factor of 3. So it's a horizontal shrink by a factor of 3, or in other words, a factor of 1/3, because horizontally it's going to be 1/3 as large. Likewise, dividing by 4, I would think that would shrink it, but because it's on the input, not only does it move horizontally, but the input does the opposite of what we expect. So it is actually going to be a horizontal stretch by a factor of 4. Let's look at these in action. So the way we write the vertical stretch, that's g of x, is 2 times f of x. And what we're going to do is I'm going to start with those same 5 blue points, and each point is going to get twice as big vertically. Now when I say twice as big, that means it's going to move twice as far from the x-axis. Or in other words, I'm going to take the y values and double them. So for example, the point 1, 1 is going to move to 1, 2 because the y value got doubled. The points 2, 4 and negative 2, 4, their y values, when they double, they go up to 2, 8 and negative 2, 8. So they stretch, they're twice as large or twice as far away from the x-axis. However, the point 0, 0, it doesn't go anywhere because it twice as far, what is twice of 0? Twice 0 is just 0 again. So all these points, we're going to plot them now, and notice 0 gets put right on top of itself. The origin doesn't move. And our new graph looks stretched vertically. It's twice as tall because each of the points moved. Let's look at the vertical shrink. The vertical shrink is written 1/2 times f of x. And what's going to happen now is we're going to multiply each of the y values by 1/2. Or in other words, we're going to divide them all by 2. So, for example, the point negative 2, 4 moves to negative 2, 2. Notice it only affects the y value because it's vertical, and it's half. So we're there. Half of 1 is 1/2. 0, half of 0 is still 0, so that doesn't move anywhere. And these 5 points, we now connect them, and notice how the red graph, it's shrunk vertically. It's like it got squashed. For the horizontal, they do the opposite of what we expect. So remember, a horizontal stretch is actually going to be f of 1/2 times x. You could also write this x divided by 2. The way you do this is you take each of those original points and you're going to stretch them horizontally. So the points get twice as far away from the y-axis, or in other words, each x value of each point is doubled. So 2, 4 moves to 4, 4, and 1, 1 moves to 2, 1. When you plot all these points, again, 0, 0 will stay there because double 0, you still have 0. You notice we graph it. Our parabola looks stretched out. It's twice as wide as it was. The horizontal shrink, you're going to do the same thing, but this time it's written f of 2x. Remember, the input does the opposite of what you expect. And each of those points, well, they're going to move half as far away from the y-axis. In other words, you're going to take the y values and divide it by 2. So 2, 4 goes to 1, 4. 1, 1 goes to 1/2, 1. And 0 stays where it is, of course. So we plot these points and connect those lines. And notice we have a parabola that is squashed, but horizontally this time instead of vertically. One of the things I want you to do is just remind you or go back over how do we graph these, because that often gives some students trouble. So we have 4 examples here. What if we had a horizontal stretch by 2? Well, since it's horizontal, what we're going to do is we're going to multiply each point's x value by 2. What if we had a horizontal shrink? Well, then we would divide each point's x value by 3. What if we had a vertical stretch of 4? Well, then we would multiply each point's y value by 4 because it's vertical. And what if we had a vertical shrink by 5? Well, then we would divide each point's y value by 5. That's just the math behind what I did to plot the new points. You only ever multiply by x or y in a given graph if you're doing a single dilation. There are 2 other things we can do with this, however. We can also have a vertical reflection or a vertical flip, or we could have a horizontal reflection or a horizontal flip. Let me go through those 2 very briefly. The way you flip a function or a quadratic vertically is you use a negative. And of course, since it's vertical, that's the output. So the negative is going to go outside the parentheses. See how it's negative f of x. I'm going to take those 5 points and I'm going to multiply each of the y values by -1. That flips this over the y-axis. And the new points are down there. Notice this also is what happens when a, or the value in front of the x squared, is negative. It flips this graph vertically. As for a horizontal flip, well, that's not as exciting, and you rarely see that with quadratics. It's written like this, f of negative x. Notice the negative is on the inside of the input. And so I have my original 5 blue points, and I'm going to take each of those points and I'm going to multiply their x values or input values by -1. However, notice what happens when I multiply each of them by -1. Well, they just switch places. So the horizontal reflection of the parent function, or the flip over the y-axis, is actually the exact same graph. Now, that is not interesting at all when it's a parent function, but when you've translated the graph left or right, then a horizontal reflection is actually interesting. So you will see it occasionally. But most of the time with quadratics, you'll only see the vertical reflection or flip over the x-axis. And those are all the things you can do to the parent function f of x. Thank you very much for watching.